My name is Xiaocheng Liu from University of Southern California. Today I'm introducing Gnome, a system that improves GPS accuracy in urban canyons. So pretty similar problem like the previous one. So the work is in collaboration with Sumanas from Microsoft Research and my advisor Ramesh Govindan. So GPS positioning is important to many applications like navigation, Internet of Things, and location-based services. However, when the device is in urban canyons, the accuracy will drop a lot. So now Mr. Simpson is downtown Los Angeles, and this shows the map service on his smartphone. We can see the reported location is far from the actual position. In this scenario, the error radius is usually very large, and the ground truth is sometimes even out of the radius. The bad GPS accuracy affects many applications. For example, Uber. The positioning arrow may drop the pickup pinpoint at a very different place, well, usually across the street. Then there will be an angry call between the passenger and the driver, like, where are you? Have you arrived yet? So our goal is, So why does GPS perform so bad in urban canyons? To understand this, I need to explain how GPS works. So the fundamental idea is that there are several satellites around the Earth keep broadcasting their locations and current time. Once the receiver gets the signal, it can compute its distance to each satellite by multiplying the signal propagation time and the speed of light. Definitely there will be some extra computation inside, but it's already included in the GPS module. Then the receiver can get its own XYZ location by solving the triangulation problem. In practice, the more satellites we get, the less error we will have. In Mr. Simpson's case, the main reason for his positioning error is non-line of sight signal. GPS receiver assumes all signals travel in line of sight, like this. However, the buildings could block or reflect satellite signals. So if the line of sight path is blocked, the signal may be reflected to the receiver, and we call this non-line of sight. From this figure, we can see that the non-line of sight signal travels longer than a line of sight signal, which is called path inflation. This means it has longer propagation time, and the receiver will compute a longer distance to the satellite. In the line of sight scenario, the receiver can compute every distance correctly, so we have high accuracy. If some of the signals are in non-line of sight with path inflation, the positioning result will be very different. Here, it shows a wrong position calculated with path inflation. In practice, the path inflation can cause error larger than 100 meters. Therefore, if Mr. Simpson's phone can correctly estimate the path inflation for each satellite signal, it will compute a more accurate position. Can we do this? Yes, we need a Gnome. There are three challenges for the Gnome. First, how can we trace the satellite signal and compute the path inflation? Second, with the path inflation known, how can we find a location that is close to the ground truth? Third, how can we perform these computations on a phone in real time? Gnome has three solutions to solve those challenges. First, it performs building height estimates with publicly available 3D models to accurately estimate the path inflation. Second, it searches most likely ground truth position from a set of candidates around the original GPS output. Third, Gnome pre-computes path inflation maps in the cloud to speed up the localization process on the mobile device. In our test, Gnome reduces the positioning error by up to 55% on Android phones in different cities, with more than 15 Hz of running speed. Let's take a look at the first challenge. There are two keys to for path estimation. First, we should know where the satellite is. This information is already encoded in the signal. Second, we should know the 3D model of surrounding buildings and use ray tracing technique to track the signal path and simulate the effects of its encounters with the building surfaces, like blocking or reflection. By knowing the signal path, we can calculate the path inflation by comparing with line of sight case. Existing works usually use commercial 3D models or use the depth camera on mobile platform to get the 3D model. But these two approaches are not scalable. Commercial models may not be available for all cities, and car-mounted camera can be expensive to own and operate. We find that Google Street View, as a worldwide street-level image database, also contains the depth information for most cities. These models can be simply downloaded from Google using the viewpoints latitude and longitude. Here, the viewpoint means the Street View car's location when the images are taken. The major issue with Google's model is that some building surfaces are either missing or too short, especially for tall buildings. This is caused by limitation of Street View collector's hardware or its model extraction algorithm. So this image shows the model planes in different colors, and the red lines shows the actual height of that buildings. If the building surface is incorrect, some signals retracing result will be different. For example, the receiver position is shown in green pinpoint, and the satellite signal from the white satellite will be considered as line of sight if we use the default model. Therefore, we will not do path mitigation for it, and we will have a different result. So we should try to estimate the real shape of those building surfaces. First, we use image segmentation to detect the skyline and the top of each building. Then, we use the pixel position of the building's top to compute the elevation angle from the viewpoint. Third, since the viewpoint location and the building's location are already known to us, we can calculate the building's height using the elevation and the distance from the viewpoint to the building. Finally, we repeat the estimation with 3 nearest viewpoints from the building and use the average height as output. Here it shows the height estimation from the first point. And here it repeats the process at the second point. And then third, the adjusted height will be added back to the 3D model for following process. Now, let's take a look at the second challenge, doing decision. First, we find that recent Android OS starts to provide the raw GPS data, like satellite position and signal propagation time. We leverage such information to recalculate the position after path adjustment. With satellite position, signal travel distance, and accurate path inflation, we can remove the inflation part from the signal and recompute the adjusted location like this. So if we can get correct path inflation, we can get a more accurate result. However, estimating correct path inflation relies on the ground truth position where the receiver is. But we can never know this. Instead, the receiver position is what we want to find. So how to do that? If we do retracing from a different candidate point that is not the ground truth, we will get a very different path inflation estimate, and the adjusted location will be very different. We can see that the path inflation in yellow is much longer than the one in the red. Since we don't know the ground truth, we can try several candidate points around the reported location. At each position, we can compute the path inflation and the adjusted position. The distance between the candidate position and the corrected location is called location adjustment. From experiments, we found that the candidates closer to the ground truth usually have a smaller location adjustments. This is because when a candidate is close to the ground truth, its path inflation is more similar to the one to be done at the ground truth point. In contrast, if the candidate is far away, we will have a wrong reflection calculated and will be added to the satellite path. Then the final location will be unpredictable and will be even further from the true position. With the insight of location adjustment, we propose our candidate selection algorithm. First, we choose several candidates near the original GPS output within the error range. For each candidate, we calculate its location adjustment, shown on the map. And finally, we find the one with minimum location adjustment and use that as the output. The situation in practice is a little more complex, so we design a clustering algorithm. Please read our paper for details. Now, let's see how to do this on a phone. The major problem is that estimating path inflation is too heavy for a phone. A desktop server needs tens of minutes to do ray tracing for all the candidates along a street. So we cannot do that on a phone. Instead, we can pre-compute this inflation on the cloud and load it onto a phone. For each candidate on the street, we compute the ray tracing result from the satellite from any angle on the sky. Specifically, we enumerate every azimuth and every elevation and use that as the satellite position. And we do ray tracing with 3D models and get the path inflation. The result will be stored in a dictionary data structure. We repeat this process for the second candidate and the third candidate and all the other candidates in this area. The indexed inflation data will be stored in a model file. The size of model file is usually a few megabytes for 1 square kilometer area. This inflation model is preloaded to the phone. When the GPS data comes, Gnome will find the candidate points around current location and read its past inflation values. Then it uses candidate selection algorithm to do positioning. Here is the complete pipeline of Gnome. The cloud part downloads data from Google and computes the inflation. The mobile part runs the localization with GPS input and inflation data. Finally, I will briefly describe the experimental results to quantify the benefits of Gnome. We collected walking trace and GPS data from 4 cities, Los Angeles, New York, Frankfurt, and Hong Kong. Gnome app runs on 4 different Android devices in those places. In the test area, most of the observation points cannot see enough number of line-of-sight satellites. This means the sky view has really made a lot of occlusions. In Los Angeles, we tested 3 scenarios: static, walking, and driving. We can see that Gnome outperforms both Android and iOS in the static and walking scenarios. The static means the user stands on a point for a few minutes, and walking and driving mean the user moves with the phone, either in the pocket or on the car's dashboard. Note that we are comparing Gnome with the original phone's output. So that means the phone's output will also have many optimizations, like common filter and map matching and dead reckoning. In the driving mode, we can see that the stock phone's accuracy becomes much better. This is because the high-speed driving can help the phone's internal optimizations, like map matching and dead reckoning. We also conducted Gnome experiments in different parts of the world to show that it's scalable. From this figure, you can see that the result is consistently better than the default output from the phone. And Gnome also outperformed the state-of-the-art solutions. You can read our paper for detail. For the speed, on the cloud can process 40 minutes for 1 kilometer street. And on the phone side, we can do 15 hertz which means can satisfy most real-time applications. In conclusion, the Gnome, most GPS errors comes from non-line-of-sight signals, and we designed Gnome that leverages Google Street View and non-line-of-sight mitigation to improve the GPS accuracy. In the design part, we corrected the building height from Google Street View to improve the accuracy, and also pre-computes all the path inflation to make the mobile part run fast. In the test, Gnome outperforms the default output of both iOS and Android phones. So that's all about my talk. I'm good to take questions. Thank you very much.